Hi everyone, I am Ashfaq Iftakher. I'm a first year PhD student at Texas A&M University. Thank you for your interest in our work on driving force-based design and control performance analysis of reactive distillation columns. So here is an outline of the presentation. I will start with the motivation of our work. Then I will briefly describe the integrated design control framework that we have proposed. After that, I will demonstrate the key features of the reactive distillation design control toolbox. Then I will show the application of the toolbox and the framework with respect to a case study, and then I will draw the conclusion. So what is the motivation of the work? Here we can see that for the production of methyl acetate, the Eastman Kodak company were able to bypass a series of separators and reactors, and then they were able to achieve higher product purity by incorporating all the separators and reactors in a single intensified process unit, which we denote as a reactive distillation column. Some of the key advantages of these RD process units is the improved selectivity and productivity, because we are continuously removing product from the reactor domain. One of the obvious advantage is that the fewer number of process unit is required, which translates to reduced capital cost. And since we are using the heat of reaction inside the RD column for the separation of the product, we require lower number of energy. However, there are some design and control issues that has to be taken into account. Since this is an intensified process unit, we're losing the degree of freedom. Consequently, the operating window gets narrower. In other words, controllability of the reactive distillation columns strongly depend on the design. Therefore, it is of paramount importance to incorporate the operability and the controllability of these intensified RD units in the early design stage, so that a feasible steady-state and dynamic simulation or the operation of these columns are possible under process of set. So here our work comes into play. We take all these issues into account and propose an integrated design and control framework. So in our proposed integrated design and control framework, there are 3 steps. In the first step, we define the problem, we define the objective function, and we represent the reactive system in terms of elements. In the step 2, we integrate the design and control of the RD system. Using the driving force approach, we determine all the key design parameters using the driving force diagram, and then we determine the optimal control structure. In step 3, we verify the determined control structure in step 2, and after that we perform the dynamic simulation under both PI and NPC controller. And at the end, we determine all the objective function parameters, and based on the parameter values, we select a final design. So the objective function is a multi-objective function that takes into account both the design and control aspect. Here we minimize 6 independent metrics. Here J1 is the total energy consumed by the process, and J6 is the total carbon dioxide footprint per kg feed. These are our design metric. J2 is the integral absolute error, and J3 is the total number of valve travel. These are our control metric. And finally, J4 is the relative gain array, RGA, and J5 is the Nidelinsky index. These 2 metrics verify the control structure and also how stable the system is. It also determines system stability. Then we proceed to the reactive system representation in terms of elements. So elements are the transform variables. These are the ratio of the linear combination of the components in a specified phase. Here we see that if we have a component I in phase beta, we can perform a linear combination and then get an element-based mole fraction in phase beta. An obvious observation is that the reaction stoichiometry is embedded to the elements through the coefficient of the component. Here the coefficient is Aji, which is the number of moles of component I in element J. Elements are useful for the representation of RD columns because these are used for the simultaneous calculation of physical and chemical equilibria. which are required for the design of RD columns. An immediate application is that the number of elements is less than the number of components and is exactly equal to the number of component minus number of independent reactions. So the driving force, the definition of the driving force can be derived both in terms of component and element, and it is the difference between the element or component composition between coexisting phases. For example, let's say we have an element I in vapor phase and in liquid phase, then driving force would be the difference between these two compositions in these two phases. If we define driving force in terms of component, we can use this diagram for the design of non-reactive systems or the traditional distillation columns. If we define driving force in terms of elements, we can use or follow the similar procedure for the design of reactive systems. Here is a typical driving force diagram that can be used for the design of non-reactive systems. Here we can see that the driving force is generally concave upward, and there exists a point where the driving force is maximum. This is our point of interest, and we are also given the light component composition in both the distillate and at the bottoms, and then we calculate the slope of these connecting lines, and after determining the slope, we can determine the minimum reflux ratio and the minimum rebel ratio, from which we can determine all the key design parameters. Similarly, if we construct driving force diagram based on the elements, we can follow this exact same procedure for designing our reactive systems. So some of the key parameters can be obtained includes the feed stage, which is exactly dependent on the location of the maximum driving force, as we can see from this relationship. So after designing the RD column base force, we do the hysteresis simulation. After performing the simulation, we export to the dynamic model, and for the hysteresis analysis, we linearize the dynamic model and then construct our state space model. So the state space model is basically expressed in terms of our state vector, our input vector, our output vector, and these constant matrices. An important fact is that this A matrix is our system matrix. It is a square matrix, and from the eigenvalue of this square matrix, we can determine whether the system is stable or not. In step 2, we calculate the hysteresis gain matrix. In step 3, we calculate the RGA or relative gain array. RG indicates the degree of loop interaction. Then we calculate the Niederlinsky index, and also we calculate the eigenvalue of the system matrix. These together indicate the system stability. Then we proceed to a dynamic analysis. In the step 1, we perform the open loop simulation to check whether a new steady state is reached. Then we perform our closed loop simulation under both PI and MPC controller. Here is a process controller block diagram that highlights the application of both the PI and MPC controller. Here the rigorous dynamic model is derived based on the driving force, and it experiences an external disturbance. Under the process offset, the error is set to the controller. There can be two different kinds of controller. For the MPC, we provide the linear model of the process. The controller gives an output to the valve, and the process is adjusted accordingly. To perform all these steps and link between the design, simulation, and control softwares, we have developed an RD design control toolbox. Here is the work data flow of the RD design control toolbox. As you can see, in step 1 and 2, we can automatically generate the flow sheet for the hysteresis simulation in either Aspen Plus or Pro 2. In step 3 and 4, we can basically generate the hysteresis model and also perform the hysteresis analysis. And finally, in step 5, this toolbox allows the auto generation of MPC script. Thus, the dynamic analysis can be performed in MATLAB and the dynamic responses can be observed. To explain all these steps deeper, we see that the problem can be set up very fast. So let's say we want to set up an RD column in our RD design control toolbox. In order to do so, at first we select the components that are present in our RD column or RD system. Then we proceed and define the number of inlet. Then we define the reaction conditions. And finally, after providing all this data, we can click on the generate Ashfaq file, and this button translates all this data into an Ashfaq Plus Ashfaq Plus process flowsheet. This flowsheet is well defined and is ready for the stress simulation. After performing the stress simulation, the dynamic file is exported to Ashfaq Plus Dynamics, where the control design interface script is auto-generated. We define the top control and bottom control variables and then click this generate CDA script. Then our control design script is generated in our local directory. If we export this script into Ashfaq Plus Dynamics and invoke this script, the SRSpace matrices are generated in our local directory. Another key feature is that after exporting all the nominal value of the manipulator and control variables and providing all the controller parameters like the prediction horizon and control horizon, if we click on the generate MATLAB MPCM file, a MATLAB file is generated in a local directory. We can just load this file into MATLAB. As you can see that the code is automatically written, the user doesn't have to write any code. And after running this MATLAB file, we can perform the MPC closed-loop simulation and data is stored in an Excel file in the local directory. So all these steps are highlighted in 6 case studies. Here I will be showing the production of MTBE with the presence of inert, while the other 5 case studies are reported in one of our earlier publications. So at first we formulate the problem. MTBE or the methyl tert butyl ether is produced from the reaction of isobutene and methanol under the presence of 1-butene. We define the design target. More specifically, at the bottom, MTBE should be produced more than 90%. We specify the feed conditions and flow rate. After that, these molar compositions are expressed in terms of the elements. Here we can see that the number of component is 4 and the number of reaction is 1. So the whole reactive system can be expressed with respect to the 3 elements. Here is the formula matrix. After formulation, we proceed to the design of the RD system. We construct the reactive VLE phase diagram. And from the phase diagram, we construct the reactive driving force diagram. As we can see that there is a point where the driving force is maximum. We denote this point as the RD design at point A. And we compare this RD design and control at point A with respect to another arbitrary point at point B, where the driving force is not maximum. Then we construct the reactive McCabe-Thiele diagram. And from the reactive McCabe-Thiele diagram, we are able to determine all the key design parameters both for point A and point B. Note that at point A our driving force was maximum and at point B our driving force was not maximum. Then we proceed to our stress simulation and analysis. For the RD design at point A, we calculate our relative gain array. We see that the diagonal elements are close to unity. our needlelicity index is positive and real part of the eigenvalues are negative, implies the system is stable. Similarly, for the RD design at point B, even though the real part of the eigenvalues is negative and the system is not unstable, we can see that the diagonal elements, is greater or goes further away from unity, which means that the design at point B encounters larger degree of loop iteration compared to the design at point A. Then we proceed to a dynamic analysis. We perform the open loop simulation and check a new steady state is reached for both the top loop and the bottom loop. Then we perform the closed loop simulation under PI controller. On the left, we have the RD design at point A where the driving force was maximum, and at the right we have the RD design at point B where the driving force was the maximum. We can see that at the maximum driving force, the controller is able to reject the process disturbance very fast compared to the design at point B, which can be further highlighted by the value of the valve travel. As you can see that the design at point A is better under PI controller. Similarly, we perform the closed loop simulation under MPC controller and we observe similar qualitative results, that the design at point A where the driving force is maximum is able to reject the disturbances better or more efficiently than at point B, because the number of valve travel is significantly lower here at point A than for the design at point B. To combine these results and after determining all the objective function parameters, we can see that the total number of energy consumption J1 is lower for point A compared to point B. Similarly, total number of carbon footprint per kg feet is also lower at point A compared to point B, and all the control matrices are better at point A compared to point B. In other words, the design control solution where the driving force is maximum, which we are denoting as the RD design at point A, is better than the alternative design at point B. In conclusion, we can say that we have provided a systematic framework for the integrated design and control of RD systems. We have also developed an integrated design control toolbox that assists the user in setting up the problem, generating the matrices, and writing all the scripts for the MPC closed loop simulation. We are showing that the design parameters at the maximum driving force translates to superior controllability under both regulatory PI and supervisory MPC controller. And one of the immediate future work is the inclusion of the integration of design and control for peg loop and dividing wall columns. And also we plan to extend our reported toolbox to handle distillation columns with or without reaction, and also the side reaction, and also the side stream. So here are some of the references. Thank you.